Hi, I am Lee. I will describe simple methods to represent shapes with sample spheres, with my co-authors Arjun, Shally, and Tarun. I have a paper in Chi 2020 about synthesizing element patterns. Users can specify a sparse set of elements, and the system can automatically fill in the rest of the output domain. A core part of the method is to represent element shapes with sample spheres. However, in the Chi paper, the samples are manually placed by the users, which might not be desirable for real applications. Thus, our goal is to automatically generate sample spheres from given shapes, so that users can directly load different graphical elements for pattern synthesis. This problem has a long history in computer graphics, with applications in simulation, rendering, and modeling. In addition to automatic computation, the samples should accurately represent the shapes. The computation should be efficient and simple to implement. The number of samples should be small, and controllable depending on the intended applications, such as whether the shape is rigid or deformable. Now let's talk about our two methods, with different characteristics in representing shapes with spheres. Our first method selects polar balls along medial axis as sample spheres. Medial axis is like the central skeleton of the shape. Polar balls are centered at the medial axis, and their radii are set up so that each polar ball touches multiple points on the boundary of the shape. We select the polar balls in decreasing sizes, since larger balls tend to better represent the shape. We can tune the density of the balls by thresholding their overlaps, so that no two balls are closer than a given threshold. Our second method is based on k-means smallest enclosing circles. We start by placing points uniformly over the shape, and initializing a given number of sample spheres. The sizes and locations of these spheres will be optimized iteratively. In this toy example, we use two sample spheres visualized in red and green. In each iteration, we assign the nearest sample for each point, and update the sample spheres as the smallest enclosing circles for each point set. The iteration can continue until sufficient convergence or reaching a certain time limit. Our two algorithms have different behaviors. Intuitively, the MAT method fits more sample spheres within the shapes, while the SEC method generates less spheres covering the shapes. It is possible to have more samples with better fits for the SEC method to achieve properties similar to the MAT method. Thus, that is our default choice. We can optimize the number of samples based on a set of objectives, including overlap between samples, areas outside the shape, the number of adjacent samples, and symmetry of the shape. More details can be found in our short paper. We could not release our source code right now. Fortunately, our methods are very easy to implement. With open source code, it took me only a few hours to implement both methods. Here are some results produced by our SEC method with optimized number of samples over a variety of shapes. Here is a comparison with the current automatic pin placement method for Puppet Warp in Adobe Illustrator. Our method can place samples better represent the shapes. Our methods could appear in a future release of Adobe products and directly benefit many users. We plan to investigate applications of our methods in 3D, and perform more analysis and comparisons. Thank you.